All right. Good morning and welcome to the Warren seminar. So it's my great pleasure today to introduce Professor Kelemen, who is going to who is the today's lecturer of the seminar. So let me say a few words about him. So Peter Kelemen is the Arthur Stork Professor at Columbia University in the Department of Earth and Environmental Sciences, which is based in the Lamont Doherty Earth Observatory. A few words about his scientific career. So he started his undergraduate studies. He did his undergraduate studies at Dartmouth College, and then I read that he spent about 1 year in India doing some geological mapping in the Himalaya. After that, he pursued his studies at Washington University, where he obtained a MS and a PhD degree, and the PhD degree was in 1987. After that, he moved to the Woods Hole Oceanographic Institution, Massachusetts, where he spent about 16 years as a research scientist. And then in 2004, he was offered a chair at the University of Columbia, where he has been here since. So in his early career, and most of the time he was working, he has been working on his research has been on the genesis and evolution of the Earth crust in ocean basin and continents. But for the last 15 years or so, I think his work has been focused on this topic that is going to be today's seminar, which has been studying the natural and engineered system of removing CO2 from the atmosphere and also storing it geologically in rocks which are rich in magnesium and calcium. So I should say that his work has been one of the most active proponent of this technique, at least studying this idea of storing carbon in mineral form in mafic and ultramafic rocks. And I should say that it's actually an article about his work, that gave us the inspiration to bid for this EFRC center, and that was granted a few months ago. So his work has been recognized by multiple awards. I would just say that he is a fellow of the American Geophysical Union, and is a recipient of the AGU Bowen Award, but last but not least, he has been elected to the US Academy of Sciences in 2014. So please join me to welcome Professor Kelemen.
So it's a pleasure to be here and to visit this very impressive facility. I will say that I have lots of friends in the Earth and Environmental Sciences department, and I've been there many times, but they've never brought me here. So it's pretty cool. And I'm really having a great time so far. I'm sure it's going to be a fun visit. Okay, so there's just one person's name down here, but as Professor Detourné mentioned, I've been working on this for, too long. It's embarrassingly long time. And lots of people have been involved, and so I guess I won't take up your time reading all these names, but just know that the things I'm going to be presenting to you are the result of lots and lots of people's work. And then I'm going to now show you 93 more slides in 50 minutes. So please fasten your seatbelts, put your tray tables in their locked and upright position. Okay, so first, it's always good to, in this particular kind of topic, to remind ourselves what we're up to and why it might matter to more than just geoscientists. And so this is a figure from the UN Environmental Program that's been repeated all over the internet and received a lot of general agreement from the IPCC and other organizations that are, somewhat conservative in this context. And so what you see here is, according to these guys, who include CalBurps, people are emitting 50 billion tons of CO2 and CO2 equivalent per year already. And if you just extend that trend forward, of course, it looks like there's going to be lots of greenhouse gases in the atmosphere. And then this red line is somebody's idea, should have huge uncertainty envelope around it, of what needs to be done in order to keep warming from exceeding 2 degrees compared to the pre-industrial time. And so the green is essentially involves capping all the emissions that can be capped either by switching to renewables and nuclear electricity generation, for example, or by capturing CO2 from smokestacks, not only at fossil fuel power plants, but also cement and steel factories. And because those facilities are still being built and they're intended to last for decades, there would be quite a bit of carbon capture and storage in this scenario. So then the dark brown, they don't think is very easy to mitigate, CalBurps and so on. And then the little bit of remaining CO2 emissions they have out here at the end of the century is things they think are very hard to mitigate, like airplanes. And so because the net of the brown and the lighter brown doesn't fall below the red line that they think is the limit for emissions to reduce warming, they end up with this blue zone, which is negative emissions, where we're actually going to have to take CO2 directly from air. And they're saying that you need to do about 10 billion tons a year of CO2 removal from air by the late 2050s, and about 20 billion tons by the end of the century every year. So how much should you pay for that? And what's kind of funny in a way is the California Low Carbon Fuel Standard is now paying $200 a ton for CO2 stored, sometimes removed from air, but stored. Whereas the cap and trade system in California is paying about $20 a ton. So obviously, even within California, there's no consensus on exactly how this should be managed or what it's worth. I like this diagram. This is the White House Interagency Working Group and later the EPA report on the so-called social cost of carbon. And so this is dollars per ton of CO2 added to the atmosphere, damage per ton of CO2 added to the atmosphere along the horizontal axis. And this is probability on the vertical axis. And that's why I like this, because it doesn't present a single number. The different colors are for different discount rates, or you can think of this as growth rates of the economy, real growth rates of the economy. And so they have all these different probability histograms for different economic growth rates. And in particular, for talking to students, I think it's important to emphasize the uncertainty in all this. But of course, if you were a policymaker and you had to design a system with a tax or some kind of incentive, you're going to lock on right away, say, well, the economy has been growing 3% in real terms my whole life, and probably will continue, we hope. And so, and I'll just look at the average, which you'll notice displaced significantly from the peak probability because of this fat tail out here. But I'll just pick that average value. So $42 a ton. And this number has been floating around for long before I got involved in this field. Okay, so a few years back, Jen Wilcox, who's, among other things, is a great convener of humans, held a conference in Calabria, and it wasn't just the usual suspects. There were lots of people from coal companies who had been paid for a decade or two to figure out how to mitigate CO2 emissions from coal-fired power plant smokestacks. And they would show figures like this, where if you spend a lot of money but you only remove a little bit of the CO2, obviously that's quite expensive. And then you have some minimum cost per ton of CO2 at some median amount of CO2 removal. And then if you insist on removing every single gram of CO2 from the gas going out of that smokestack, then it gets very expensive again. And so $42 a ton turns out to be about 60% of the CO2 in the flue gas. And they understood what they were doing very well, and they would give these presentations. Oh, it's not, that's sad, it's not in focus. That's almost the opposite of what's intended here. Well, anyway, so at the same meeting, there were what I like to describe as Europeans in tight pants who are doing integrated assessment models. And so they're focused on that. There's a climate model in there and an economic model in there and so on. And they're basically trying to generate scenarios that keep warming below 2 degrees C or sometimes 1.5 degrees C. And they're the kind of people who are saying, well, you have to have net zero by the end of the century if we're possibly going to maintain warming below some level that they regard as catastrophic. And it was just really interesting because the coal company engineers did not like these talks. And I was watching this. They couldn't talk to each other. They just couldn't communicate. And so I was watching this and sitting in the back of the room and wondering, how we might be able to bridge this kind of communication gap. And so on the one hand, right, we have the UN Secretary General and the President of the United States referring to climate change as an existential challenge or an existential risk. And on the other hand, we've got various other speakers who are not dumb saying this is not true. So one analogy that's been used and a little bit overused is suppose that astronomers discover a meteorite that's 3 years away from potentially crossing Earth orbit. And initially they're not too sure, maybe there's a 30% chance that this thing is going to hit the Earth. Scientists being who they are, there'll be a group that's funded by the Heritage Foundation who says, no, it's only a 2% chance, and there'll be a group that's funded by Bill Gates that says it's a 90% chance. And so maybe that's not the right person. But anyway, someone. And so, some things. You know that every day you wait, it'll be more expensive to fix this problem. You know that every day you wait, you'll have a better idea of how much you need to spend. And you know that every day you wait, there is a day somewhere out in the future, but you don't know when it'll be too late. So in those ways, it has a lot of analogies to the climate problem. And so based on a probabilistic analysis, a group of scientists come up with the idea that we should spend $42 per ton of meteorite. Okay, now, this is where the analogy actually breaks down. Because I don't know what different people mean by existential threat. But that sort of $42 scenario probably includes things like this. So climate risk isn't binary. The meteorite either hits the planet or it doesn't. But climate risk has all sorts of intermediate outcomes that are bad, but not as bad as every single person dying. This particular study, with God only knows what uncertainty, concluded that a sort of business as usual scenario would lead to an annual death rate that's comparable to deaths from all infectious diseases combined. Is that an existential threat? Is that a catastrophe? That's up to you. That's a philosophical question. But okay, so if you're prepared to accept that, then maybe $42 a ton is the rational number for a carbon tax. But what's over there? So you'll see there's actually finite values going off the right-hand end of this diagram. And so this is what I did sitting in the back of the room with watching the coal company engineers and the integrated assessment modelers duke it out. Was I said, okay, well, I'm going to put a fat tail on this distribution. So now we're looking at the same probabilities, but on a log scale. And then I just stuck in these very, very low probability outcomes that have higher and higher costs. And out here is everybody dies, and not everyone dies because then money wouldn't have any meaning. So these are the two people who are still around with their windmill and their refrigerator. But 10 billion people have just died, and we'll assign them a value of $1 million per person because that's how much the average American spends on health care in their life. And I gave this some probability that wasn't zero, but in any case, it comes out to $100,000 per ton of CO2. And then the nature of this kind of fat tail distribution is that if I then recalculate the average cost, it's $600 a ton and not $42 a ton. Now, I'm not saying that this is the right answer, please understand. But what I am saying is it's kind of a philosophical issue. How do you want to respond to this kind of risk in the face of considerable uncertainty? So here's this scenario, and there's a lot of carbon capture and storage up here, which is sort of relevant to the talk today. But there's also 10 billion tons of CO2 removal from air by mid-century. And so let's imagine that that part costs $100 per ton of CO2 times 10 billion tons is $1 trillion a year, is about 1% of global GDP. So maybe that sounds like a lot. So maybe that's the last resort. If you wait, it will be too late to know, right? So this is a nice analysis from Goldman Sachs. And over here, over where I am standing, is the less expensive things like turning out the lights in the big buildings that actually saves money. And then various mitigation strategies that are immediate. And so they're looking at the expensive end of the mitigation curve. And they're saying for this last 10 billion tons of mitigation or adaptation, the cost gets very high to mitigate these last 10 tons of emissions. So in here, you might have big trucks and various large industrial things. And out here, you've got airplanes and cowburps and what have you. And so what you can see is those costs become very, very high. And if you can avoid them, you save trillions of dollars a year. So all of a sudden, $100 a ton or even $250 a ton looks like a bargain. So if you think that there's an existential risk with a probability that's not zero, and you think that this might be a good idea, then actually removing CO2 from the air might be a relatively less expensive option than mitigating every single bit of emissions. So that's all the philosophy we're going to get. I'll talk to you about some geology, and then engineered systems for CO2 removal from air, and that are kind of mitigating these natural systems, and then systems for solid storage of CO2, and then some chemomechanical feedbacks of the type that your group here is probably pretty interested in studying. So not all of you are geologists, so I'm going to teach you some words. Peridotite is a rock type rich in the mineral olivine, which in our lecture today is just magnesium silicate with 2 moles of magnesium per mole of silicon. The gemstone name for olivine is peridot. There it is. It's the August birthstone. Some of you should have some. And that's why rocks rich in olivine are called peridotite. The Earth's mantle, which is most of the silicate Earth, is composed of peridotite. And when peridotite gets hydrated, it forms hydrated magnesium silicate serpentine. And sometimes there's excess magnesium, magnesium hydroxide or brucite. And when these materials react with CO2, you can make calcite. I don't have any calcium on this diagram yet, but I will. Also known as limestone, magnesite, magnesium carbonate, and dolomite. And finally, travertine is chemically precipitated calcite, and you'll see what that is. Okay, so the Earth's mantle is normally shielded from the atmosphere and the oceans by the ocean crust, 7 kilometers thick or so, and the continental crust, 40 kilometers thick or so. But sometimes plate tectonics does us the favor, in one way or another, of pushing those rocks toward the surface and then faulting and erosion expose them. And the peridotite is really, really far from equilibrium with the atmosphere and surface waters and the ocean. So when you do this, you have this huge chemical potential gradient across that surface. It's like a giant battery. And the notion here, in essence, is to use that chemical potential energy to reduce the cost of carbon management. So another way that that happens is that magmas arise by partial melting in the mantle, and they go to the surface. And they, like peridotite, they're also rich in magnesium and also in calcium. And they're also really far from the atmosphere and the ocean. So when I'm talking about peridotite, if you would prefer, you can think about basalt. So carbon mineralization, this idea goes back to somebody named Seifert or something in 1990, and then Klaus Lachner. You take magnesium or calcium-bearing minerals, typically magnesium or calcium-bearing silicates, react them with CO2 from air or surface waters, and make carbonate minerals, magnesite, calcite. And these are inert, they're non-toxic, and they basically store CO2 for permanently from the perspective of a human lifetime. Okay, and to get a little more specific, I'm not sure if I like wandering around with that pointer. To get a little more specific, we take olivine and react it with CO2. We make magnesium carbonate and quartz. This is pretty fast at high temperature, and basaltic glass also goes at about that rate. Not every kind of lava, but glassy lavas. And then when we hydrously alter that olivine, because of course it's not in equilibrium with water either, we make serpentine, which is really pretty slow to react, unfortunately. Perhaps because it's closer to equilibrium with the atmosphere and the ocean. And brucite, which is really fast, especially at low temperature. That's a good target. Okay, one more bit of chemistry, because I'm going to show you some pictures that require that you understand this a little bit. So olivine and calcium magnesium silicate in the mantle. There's not a lot, but a few percent. Reacts to form serpentine, which we already saw, and dissolved calcium in water. So again, olivine, calcium magnesium silicate, water, serpentine, divalent calcium ion, and hydroxyl. So it makes these very, very high pH calcium hydroxide waters. And then that water comes to the surface, and that calcium, all the carbon is used up, as you'll see. That calcium reacts directly with CO2 from air to form calcite on the surface. Okay, so rain falls on the ophiolite. Rain doesn't have a lot of magnesium in it. pH might be around 6. And it dissolves magnesium from the rocks, and that's charge balanced by uptake of CO2 from the air in the form of bicarbonate. So that makes what we call type 1 water. People working in periddotites, pH around 8, very, very rich in magnesium bicarbonate. Much richer in magnesium bicarbonate than the rainwater that it started out. And if you drill a well in Oman or lots of other places where mantle rocks are exposed on the surface, most likely you're going to get nice kind of blue, tastes pretty good, magnesium bicarbonate water. Sometimes that just sort of travels along in a shallow aquifer. Sometimes that goes deeper. It loses contact with the atmosphere. It continues to react with the rocks. And that forms these carbonate veins in the subsurface. So all these white things are carbonate veins of various flavors. And the darker orange and green stuff is variably hydrated mantle peridotite outcrops. All of these are in the Sultanate of Oman, which is the world's largest outcrop of mantle peridotite. So the precipitation of those magnesium carbonates plus continuing hydration to form serpentine sucks all the magnesium and all the carbon out of the fluid. We used to say out here it's 0. Now we can measure it, but it's very, very low concentrations of magnesium and carbon. And this is typical, right, for hydrothermal systems, for those of you who've ever worked on them, that you get fluids that have no carbon and no magnesium left in them. And then sometimes those things come back to the surface. And we have these alkaline springs, this calcium hydroxide, rich pH 11 or even 12 water with no carbon and no magnesium in it. Hits the surface, and we call that type 2, right? And that draws down CO2 directly from air. And now I'm going to slow down a little bit. So this stuff here that looks like ice. So, okay, let me back up. These are peridotite-hosted catchments. The groundwater table is intersecting the outcrop surface here and back there. And this pH 11 plus water is coming out on the surface. Initially, it actually carves little channels in the carbonate because it's undersaturated in carbonate. But this stuff that looks like ice, that's calcite. Little films of calcite held up by surface tension, sitting on the tops of these pools of alkaline water. And if you throw a rock in here, or when it rains, they're denser than the water. So it's pretty cool, actually. It's like subduction. You can watch this films falling into the bottom of the pool. And it makes a new layer, presumably, on this big deposit of calcite, travertine, similar to what you might have seen at Mammoth Hot Springs or in Iceland or someplace. But this is not like that. This isn't hot water cooling and dumping solute. This is CO2 coming directly out of the air. So anyway, so this happened. You come back the next day after you threw your rock in here and took your cool video, and it's grown back. So when I first started working on this and I heard, well, we thought about using these rocks, but they're too slow, I thought, how can that be slow, right? I mean, it's something that happens in a day, that's like supersonic for a geologist. So let's go see how long it really takes. Okay, so anyway, so there's two places where you have CO2, direct uptake of CO2 from the air, here at the upstream end and here at the downstream end. And so something we might want to emulate is that process. Okay, and then we see CO2 uptake here, and again, when this type 2 water hits the surface. So way back when God was a little girl, we were doing a field trip in Oman, and we would just leap out of the truck and pick up carbonate whenever we saw it. And we sent all those samples to the accelerator mass spectrometer facility in Woods Hole, and maybe I kind of had an intuition, but I used to think those carbonate veins were Cretaceous. I used to think they were 95 million years old. But maybe by the time we were taking these samples, I'd learned to think differently. But in any case, only 2 of them were too old to date. Only 2 of them were older than 50,000 years. And the veins are a little bit older than the travertines on average, so that makes sense because the veins form in the subsurface, and it takes a while for erosion to expose them at the surface. And so, but basically, you get a mean age of about 26,000 years. That in itself is strange. Like, did this just turn on 50,000 years ago? That's crazy. And nothing changed there. There's weather and climate come and go, but nothing has changed there. And so, no, we think this is some sort of a residence time. These veins must form mostly in a near-surface weathering horizon, maybe 15 or 20 meters thick. And then erosion is keeping pace with that carbonation front and carrying, taking those carbonated rocks, eroding them, and pushing them out into the ocean. So this is kind of a steady state residence time that you're looking at. And we can do various things, run tape measures along recently cut outcrops and measure veins, or look at anyway, you can map all the travertines. For every kilogram of travertine you see, just looking at the chemistry of the type 1 and type 2 waters, for every kilogram of travertine you see on the surface, there must be 5 to 15 kilograms of carbonate veins in the subsurface. So we can measure all the travertine deposits. That's pretty easy, or go along with tape measures and outcrops. Anyway, we get rates on the order of 1,000 tons per cubic kilometer of rock per year, or it's easy to remember, a gram of CO2 per cubic meter per year. This isn't going to save the world. So then there was this nice DOE study. I never even knew there was a DOE lab in Albany, Oregon. But there was this nice DOE study on the rate of olivine carbonation by this group in Albany, Oregon. And since then, there have been a bunch of other experimental studies, including our own. But this fit that Georg Mader and I made in 2008, turns out, is still good. So what are we looking at? Temperature here and the rate of the carbonation reaction relative to the rate at 25 degrees C and 1 bar of air. And we fit those experimental data. So here's the effective temperature, and then these isopleths map the effect of increasing the partial pressure of CO2. So you see there's kind of a sweet spot at 185 degrees C, and then you get about almost a 10,000-fold rate enhancement from temperature. And then as you increase the partial pressure of CO2, you get an additional rate enhancement. All the isopleths sort of start to stack up at about 70 bars PCO2, and where you have about more than a million-fold acceleration of the rate compared to the weathering rate. So, and then, okay, so 150 degrees C, 1 million times accelerated rate in Oman, 1 billion tons of CO2 per cubic kilometer of rock per year. And I did this calculation in 1988 or 1987, or sorry, 2008 or 2007, and like, okay, so I don't know how you access a cubic kilometer of rock. I still don't. But if you can get a simple back-of-the-envelope calculation that gives you 1 billion tons of CO2 per year for some reasonably small volume of rock, then you know you're working on something that might scale to actually be a significant process for carbon management. And even less acceleration is still kind of nice. So now I'm going to talk to you about something that's actually quite recent that we stumbled into more or less because I'm argumentative. But I won't tell you that story. So we'll pretend that we set out to emulate the formation of those travertines. So, oh, that's interesting. Well, okay. So we have a source of alkalinity. We don't necessarily care too much what it is. I'll talk later about this. And we can think of a couple different ways to use it to either remove CO2 from air, which is what I'm going to talk about first, or to store CO2, or both. And so we can either look at superficial, we can mine the rock and grind it up. You can use existing mine tailings or potentially mine rock for the purpose of CO2 removal from air. Or we can invert that, and rather than bringing the rocks to the CO2, we can bring the CO2 to the rocks. Okay, so first, for 2 slides, I'm just going to talk about this in situ method. I worked hard on this. If you want, we can go into, it's not easy. We can go into the details, but I'm not going to today. So basically, the idea is you have a couple of holes. Water's moving through this network by thermal convection because you can't afford to pump. It looks a little bit like this old Wikipedia picture for a geothermal power plant. And indeed, you might be able to mine some low-grade heat out the upflow. But anyway, this water is spontaneously going down. It's reacting with these rocks. All the CO2 is removed. It comes to the surface. It takes CO2 out of the air. It turns out this is actually pretty hard to do. But anyway. So instead, let's focus on tailings for this part of the talk. So this is something that Greg Dipple at the University of British Columbia has been working on for a long time. And he's a great metamorphic petrologist and geochemist. And so I kind of often thought I would just leave this to him. But here's a picture from the Mount Keith mine. It's an ultramafic mine. We can call it peridotite. They're mining nickel there. And these are the tailings. And you can see this upper part of the tailings and also the surface, the outer surface of the deeper tailings is all cemented with magnesium carbonate. Okay? And these have only been out there for a year or so. So it's going along at a decent clip. So another reason why I thought, well, Greg is in Canada, and they have a great relationship between academia and the mining industry in Canada. And he's got lots of people that want to work with him to be carbon neutral as a mine, and that's a great goal. And we're not really storing that much CO2 right now anyway, so go for it. But from my perspective as a snobby academic, 400 million tons of peridotite mine tailings are created per year. At best, you might get 5% CO2 by weight into those tailings before you put another layer of tailings on the pile. So that's 20 million tons of CO2 per year, 0.04% of annual emissions. And it's like, okay, great, you go, Greg, but I'm going to do something else. All right? And then, okay, should you mine rocks in order to increase this number? Should you mine rocks for the purpose of CO2 removal from air? And maybe. But you're going to need, because of this 5%, you're going to need 20 tons of tailings per ton of CO2. So you can benchmark that in various ways. I like to calculate the thickness of the tailings pile over the area of Washington, D.C. as a kind of a benchmark. And so for every billion tons of CO2 from air, you're going to have a tailings pile 30 to 300 meters thick over the area of Washington, D.C. So for me, that seems like a lot. So again, not quite because we were smart, but because we were arguing, we realized that it might be smart to loop the magnesium or the calcium. Instead of using those tailings once, that it might be a good idea to use them over and over again. And even though it's quite expensive to recover calcium oxide and magnesium oxide from carbonates, for example, it's still, you can do it. And so we take, in the limit, limestone or magnesite, stick them in this calciner, derive calcium oxide or magnesium oxide. If we start with silicate, we're going to have to get rid of some silicate, but no matter. Lay it out in the weather. Again, so just like in Oman in a way. And a week to a month later, most of that stuff will have turned into calcite or magnesite again. And then you put it back in the calciner, you take the CO2 and you store it or give it to someone who wants to use it for some good purpose. and you regenerate the oxide and do it again. And so because you're using this stuff over and over again, you don't end up with a great big pile of waste per ton of CO2 removed from air, and the mining costs basically go to 0 per ton of CO2 because you use that material over and over again. It's so stupid, it's almost like embarrassing, right? So we wrote some papers about this, and we used conventional costs for energy in the United States, and calcining literature. People have been calcining limestone for thousands of years. We imagined we're losing 5% of the material per cycle. That still needs validation. We used a layer thickness of 10 centimeters, and we imagined that 75% of that would reform carbonate in a year. And this might still work if you used farm machinery, but in the lab, we have a terrible time stirring this stuff. We like to keep it wet because we have damp powder, and it climbs up the stir bars, and it just goes crazy. It's not a good way to do reproducible experiments. So that costs out at about $75 to $150 per ton of CO2 removed from air. And because Noah McQueen and I were imagining we were using oxy-fired methane as a fuel, and it's very easy to separate CO2 from water in the flue gas for oxy-fired methane, you actually generate about as much CO2 from the smokestack as you do from air, and you can sell it at about half this price. So when we published that paper, and maybe still, this was lowest peer-reviewed cost estimate for any method for direct air capture or carbon dioxide removal from air. And why? Well, because I'm dumb. I'm just a geologist, and it's so simple. It doesn't have a lot of moving parts. And there are also not reagents that you're using that you might run out of as you scale up to billions of tons. So anyway, and the area footprint is huge. So, and we were thinking, just spread this stuff out on the ground with farm machinery and stir it. And so we needed 7,000 square kilometers to remove 1 billion tons of CO2 from air per year, which seemed like kind of a lot. It is comparable to the footprint for these methods, but these methods have contactor stacks that are separated by open territory where cows can graze, but cows are not going to graze on a 10 centimeter thick layer of magnesium oxide. So I was mentioning, anyway, doesn't matter who said this, but it turns out that the Nevada test and training range plus the Nevada test site add up to about 15,000 square kilometers. And so if you did this process as we imagined it, you could use an area that size to remove 2 billion tons of CO2 from air per year, which is either a lot or a little, depending on how you're feeling. So fortunately, along came some smart engineers. And so Heirloom Carbon Technologies that you can Google is using this process, and they are going very well, and their goal is to remove 1 billion tons of CO2 from air per year by 2035. And so they have, we also, but they found that if they use thinner layers and we stick to calcium, we can 85% recarbonate calcium hydroxide in 2.5 days. So that's a lot faster than a year. But now it turns out that they don't tell you this, but I will, that this involves a 5 millimeter thick layer. So whoa, we're going to cover the entire world with a 5 millimeter thick layer of calcium hydroxide. Maybe not. So, okay, so redo this slide. Magnesium is probably 2 to 4 times slower than calcium hydroxide, so we'll just leave that for a minute. But what about the area requirement? Well, luckily, engineers are smarter than geologists, and so it's not rocket science, but they basically want to use cafeteria trays in racks. And so then you have your 5 millimeter thick. All right, anyway, so you've got all these cafeteria trays, and the CEO of Heirloom cut his teeth on robotics engineering, and so you've got little trains that are taking the trays to this calciner and then returning them to the racks. And so obviously you can reduce the area footprint a lot by making these stacks really tall. It turns out that we can remove 1 billion tons of CO2 from air with stacks of trays like that with about 500 square kilometers of area. So we've gone down by a little bit more than a factor of 10 in the area requirement. How big is that? Oops. The Denver International Airport is 100 square kilometers. So that's 200 million tons of CO2 from air per year. And the Antelope New Rochelle coal mine, the total footprint of this coal mine in Wyoming is about 500 square kilometers. I'll just briefly go back and talk about, so calcium carbonate, in the calcining step, in the heating step, you have to heat up calcium carbonate to something like 900 degrees C to effectively, in a short time, remove the CO2 from calcite. Whereas magnesium carbonate calcining temperatures are much lower, on the order of 300 degrees lower. So even in Kelvin, that's 25% lower. So that's a significantly smaller energy requirement. And we started out working on magnesium for this reason. But it's slower. So it's on the order of, so this is the magnesium rate divided by the calcium rate, with everything else being equal. And it's, it's 2 times slower or something like that. I'm not really sure. Heirloom has really locked on to calcite, or calcium hydroxide and calcite, and it is faster. But I'm not sure I understand the value proposition there. I mean, why are we in such a hurry? Just have more cafeteria trays. Because the energy savings using magnesium would be very significant. So I'm kind of pushing them to revisit that. Okay, but this scales. Okay, obviously, it's just so simple. There's tons of limestone and plenty of magnesium out there. So you could remove billions of tons of CO2 from the air per year at a cost that's, and also, we're not asking you to believe learning curves and things like that. This cost estimate, we're using kind of conventional technology to come up with these cost estimates, because this is all stuff people do. All right, so now we've taken CO2 out of the air. What are you going to do with it? And I'll talk about engineered systems for solid storage of CO2 via carbon mineralization. So again, we're back to this. I'll just briefly mention, so the first idea that people investigated, so-called ex situ carbon mineralization, you quarry the rock, you ship it halfway around the world, you grind it to 10 microns, you build a high temperature pressure reactor, you capture CO2 from a smokestack, you combine the crushed rock with the CO2 in the reactor, and you make some carbonate. Now, did the way I described that sound inexpensive? So that basically, the IPCC long ago decided that that would basically double the cost of a coal-fired power plant. And I don't think that result has changed. So there's still people working on this, and God bless them, but I don't think that result has changed. So let's look at the more geological type things. So again, we've got tailings, and we can also revisit the idea of bringing CO2 to the rocks rather than grinding up the rocks and bringing them to the CO2. And tailings is challenging because you can't really easily raise the partial pressure of CO2 on the surface, but it is not impossible, and so that's a possibility. And here we are back at Mount Keith. Whoa, why are we looking at all this again? Sorry. But I'm going to focus on in situ. So we're going to bring CO2 to the rocks now. And what's happened is we now have a source of concentrated CO2 from somewhere else, right? So we're not just relying on groundwater. Okay, now this had a bad name. The first time that I gave a talk about this with anyone from DOE in the room, he said, well, that was a really good talk, but I am never going to fund you. And this is why. This is an intimidating thing to hear. He's retired. But anyway, so this figure comes from an IPCC report on carbon dioxide capture and storage in 2005. And Sally Benson at Stanford, who's a real authority on these things, was the first author of this chapter about carbon mineralization, or I think just in general storage. So their idea is when you inject CO2-rich water or supercritical CO2 into subsurface pore space, the first thing that happens is it's trapped, you hope, beneath an impermeable cap rock. Eventually, that CO2 forms bubbles in water in the surrounding aquifer. over long times, diffusion spreads that stuff out and it's dissolved in the water. And then when your great-great-grandchildren's great-great-grandchildren start to worry about this, maybe you should think about carbon mineralization. And this is all over the internet. Just try it. You'd probably find 100 copies in 10 minutes. So fortunately, not everybody paid attention to that. And many of you have probably heard of the CarbFix project in Iceland. This is the Hellisheide geothermal power plant, which supplies some pretty significant amount of the electricity to Reykjavik. And not everybody knows that most geothermal power plants emit quite a lot of CO2 and also hydrogen sulfide. So if you're using natural steam, it's got CO2 and hydrogen sulfide dissolved in it. And when you condense the steam, you get what's referred to in the industry as non-condensable gas, but it's mostly stuff that you don't want to emit. And they vent that. So the Reykjavik Energy wanted to try to send this stuff underground. And they use a technique where they dissolve CO2 and also hydrogen sulfide in water at depth. And there's lots of cool things about this, but I won't spend a lot of time talking about them now. Anyway, and because it's a geothermal power plant, they have other wells all over the place, and they can sample fluid downstream and see what happened to the carbon. In CarbFix phase 1, they had this beautiful tracer experiment with very tight sampling, and they labeled the input fluid with carbon-14 and also with sulfur hexafluoride. And those gave consistent results. So they can see the carbon-14 enriched stuff with sulfur hexafluoride coming at the monitoring well. And they know what the ratio of CO2 was to carbon-14 or sulfur hexafluoride and predict how much CO2 should be coming out of those wells if nothing has happened. And they find that 95% of the carbon that was injected has been consumed by mineralization along the flow path. So to embody that, in this diagram, you have to actually change the horizontal axis scale by an order of magnitude, and it looks like this. And it turns out, and I've talked to Sally, this was made for a sandstone in the Gulf of Mexico that hardly had any magnesium in it. So, yeah. Don't try carbon mineralization in that rock. But if you have appropriate rocks, it can go pretty fast. So, and there are lots of reasons why I haven't plunged into the basalt study areas much, but one of them is that it's just a spectacular ongoing natural process in Oman, which seems to me indicates that the peridotite is a very favorable kind of rock to use. So not too much more to say about this. Drill, frac, drill, and then CO2-rich fluid, you hope, circulates through this system. Now we're putting in CO2-rich fluid so we can actually afford to pump if we need to, but there's also going to be some thermal buoyancy in that system, and off you go. So finally, there's reason to think that might not work. Temperature is actually a reason to think it will work, but I'm not going to talk about that today. Permeability is an issue, so we can imagine cracking versus clogging. You're adding carbon to the rock, so you're adding mass to the rock, and you're reducing the density. The alteration phases are less dense than the reactants in a lot of cases. So you're reducing the density of the solid, and the consequence is there's a big increase in the solid mass and volume. And so why wouldn't it just fill up all the pore space and come to a screeching halt? Oh, why is this here? Oh, what happened? I've got the wrong version, but that's okay. We'll just zoom through. So there's definitely potential for negative feedback here, right? But we know that completely hydrated peridotites, where every single bit of the original olivine and other minerals has reacted with water to form serpentine, we know that those are common. And in fact, it's the state rock of California. And it's also the case in Oman that there are rocks. This horizon here is about 15 meters thick, and this is about 200 meters thick. There are rocks that were peridotite where every single calcium and magnesium atom has combined with CO2. So it can happen. And we also know, and I showed you the carbon-14 data for Oman, but here's a similar system near the mid-Atlantic ridge, where carbon-14 and also uranium series geochronology indicate that these systems are active in the same place without running out of reactants, without running out of reactive surface areas for tens of thousands of years, maybe hundreds of thousands of years. So going back, Bill Fife, whom some old geologists might know, was wondering how this process of 100% serpentinization could ever work. And he proposed that because you're increasing the solid volume so much, that can create stresses that break the rock, that in turn maintain or maybe even increase the permeability and the reactive surface area in that system. So you potentially have a runaway that goes to completion. And so I'm going to show you a movie of exactly that. I'm going to show you this. This is experiments done in Oslo, or maybe in France, but by the Oslo group. And it was done in a synchrotron, so I'm going to show you an X-ray tomography movie. And they reacted magnesium oxide with water flowing from what will be the bottom to the top of the screen, forming magnesium hydroxide with a volume increase solid volume increase greater than 50%. And fortunately, they had access to this porous caustic magnesia cylinders to begin with. And so, again, the water's flowing from the bottom to the top, and as you can see, nothing happens. So this isn't a very interesting movie, is it? But then whoa! All of a sudden, the volume expansion becomes sufficient to break the rock against the hydrostatic confining pressure, and it undergoes this gigantic volume expansion. In this movie, the magnesium hydroxide is transparent, and the remaining magnesium oxide is orange. And any of you who have ever looked at a partially hydrated or partially carbonated peridotite will be thinking, I've seen this texture. Okay, so this is what partially serpentinized olivine looks like. All filled, so this looks like that, all filled with these microfractures they're full of serpentine. They're not very permeable, but they're there. Okay, and indeed, in the oil industry, this is known and invoked, for example, for the primary porosity and permeability in the Marcellus shale, because as you mature kerogen to form oil, it's light crude, right? You have a volume expansion which pushes against the pore walls, and Lash and Engelder way back calculated the stresses that would result from those volume expansions. And they're certainly sufficient to break rocks. One variant on this that we've been fooling around with again recently is that you could probably control not just that carbon mineralization in general, but you could probably pretty much control where that happens in an aquifer. So you could really, really emulate the Oman process. You could stick calcium hydroxide-rich alkaline fluid in one end of your charge or your aquifer, and CO2-rich low pH fluid in the other end, maybe supercritical CO2, and you know for sure, those are going to crystallize calcite in that zone. Might be a good way to generate some acoustic emissions, might be a good way to generate some porosity, or maybe it'll clog up. And by the way, while we're on the subject, I know how to make holes through this wall if it does clog up. And so do you, if you think about it. Okay, so I often say to oil reservoir type people, wouldn't you like to have a fracture network like that in your reservoir? Okay, so it's self-heating and self-cracking. The monitoring costs are zero because that solid carbonate isn't going to go anywhere. Potentially, we're off to the races as long as it doesn't all clog up. I'm going to accelerate because I want to get done, but it's not that expensive compared to storing supercritical CO2 in subsurface pore space. There's a startup based in Oman called 4401, which is commercializing this process. They're working on pilots in Oman and also the United Arab Emirates. I went out there 2 weeks ago for a weekend and looked at the proposed drill site in the UAE. And by chance, they had this really nice outcrop right next to the proposed drill site. This isn't always the case because carbonate's soluble in rainwater. But here, this relatively recent outcrop created by erosion in this canyon has exposed this nice carbonate vein peridotite right next to their drill site. And they've also been running bulldozers around the place to make a power line. And you see all this carbonate in these newly formed road cuts associated with the road cuts. Okay, some of you know Rio Tinto and Talon Metals are working on potentially mining nickel from the Tamarack deposit near here. And we're working with them to see if carbon mineralization can assist that process or at least mitigate their CO2 emissions in one way or another. There's a pretty significant group working with Aramco trying to store CO2 in basalts along the coast of the Red Sea. And we've been talking to some utilities, energy companies in India about storing CO2 in the Deccan flood basalts along the coast of the Arabian Sea. So this maybe finally is happening, and thank you all for your attention.
So the floor is open for questions. Sorry, just a minute.
So Peter, do you know when you said that the magnesium oxide was confined, what was the confining pressure?
They actually looked at a bunch of different confining pressures. I don't remember off the top of my head, but it was tens of MPa.
Okay.
And they actually, there's a whole interesting thermodynamic issue here. When we calculate the pressures resulting from these reactions, whether we should use the Gibbs free energy or the Helmholtz free energy, anyway, you can imagine you should sort of see if there's a sweet spot in terms of confining pressure or lithostatic pressure where this would be most effective.
I have a related question. I have a bunch of questions, but I won't ask them.
Nobody else is.
Well, so I guess, and you were hinting at this about if you have this force of crystallization that's cracking your rock as you precipitate the reaction product, and you were hinting at that if that's sealing it as you're precipitating, so you crack but you're sealing at the same time. So
I used to find that impossible to visualize. Like, oh, I've filled up this crack such that there's actually a compressive stress on the pore walls or the crack wall. And now suddenly I want water to come in here. How does that work?
Yeah.
And I was moaning about this to Alan Rubin, and he said, well, your problem is you're making your diagrams in 2D. So if you think about it in 3 dimensions, you can easily imagine carbonate pillars pushing on the crack walls with fluid going around them. Sort of like this building.
Right. Okay. I mean, I guess an analog is like quartz veins or something, or calcite veins even, where you see multiple generations of.
Yeah, a lot of times those are
precipitation.
formed in tension.
Okay. So you have some deviatoric stress that's opening it.
Right.
Okay.
Now, one reason I have lots of pictures of vein networks that are orthogonal, I call it preconceived notions because I only take pictures when they're orthogonal, but they very often are. And something to keep in mind for those of you who are interested in fracture networks, when you see orthogonal intersections, that's not an apparent intersection. Even in 2 dimensions, there is no apparent 90. It is the true intersection angle. So anyway, I take these pictures. But to me, the fact that you have 3 orthogonal sets means there's not a huge deviatoric tectonic stress or something like that that's causing that to happen.
Great talk, thanks. So what's holding this up? Is it the market forces? Why isn't this happening?
Well, I don't think I'll show you this. I have 3 slides that are pertinent to that, but I'm not sure. Actually, the fact that I'm showing you the wrong version. Oh, there they are. Okay, so CO2 storage, so-called conventional storage, injection of CO2 into pore space, is going very slowly. This looks pretty good, 8.3% per year. That sounds pretty good. But there's a couple of things about this that you need to know. And one of them is that almost all of that has been enhanced oil recovery. Way more than 90% of all of that storage was for enhanced oil recovery. And I don't know how exactly they calculate how much CO2 is left in the ground, but I'm sure they are sincere. So anyway, but that's the thing. And that's not going to go on forever, right? Because we only need a finite amount of oil, maybe less. But anyway, that will plateau. Of the remainder, a lot of that CO2 is byproduct from oil and gas production on site in an oil field. Of the remainder, most of it is from ethanol and ammonia production. And so only a tiny, tiny little bit of all the CO2 that's ever been stored was CO2 from combustion of fossil fuels, let alone cement and steel. So that's one thing. And the other thing is that 8.3% sounds pretty good, but here's the target of 10 billion tons a year, and that doesn't even count that big green area on that figure where you've got all these legacy gas-powered and coal-fired power plants that are being built this year with the intention that they should last for decades. So the actual amount of CO2 you have to store is probably up here somewhere, and this isn't getting us there. So that's the conventional story. And why is that going so slowly? Well, for reasons that aren't bad, in this country, the regulations requiring permitting a well for CO2 storage are pretty stringent. And you basically have to characterize that reservoir about as well as you would characterize an oil and gas reservoir. But oil and gas reservoirs will produce a valuable product, whereas storing CO2 is just taking out the garbage. And everyone wants to do that at the minimum possible cost with the minimum possible effort. And so there's only 2 wells in the United States permitted for CO2 storage. 2. Lots for enhanced oil recovery with CO2, but not. So that's that. And then you pile on top of that this wonderful diagram from the IPCC that's all over the internet. And the idea is, oh, this is much more complicated than conventional storage. So until we get conventional storage off the ground, why would we bother with this boutique stuff?
So we have to close here because some of us have to go to a meeting. Thank you very much, Peter, for this very interesting talk, and please join me to thank one another.